welcome to Nanotalks. My name is Ryan Ramsey, and today with us we have Dr. Christopher Allen from Oxford University, and I thank him for inviting us down to the world famous Oxford University. And today we're going to be talking about the quantification of atomic vibrations in mono-layer graphene. Very hot topic, graphene. And so thank you, Chris, for inviting us in, and I'll hand it over to you.
Okay, thank you, Ryan. Okay, so as Ryan said, my name is Dr. Christopher Allen. I work here at the Department of Materials at the University of Oxford. I'm in the group of Professor Angus Kirkland. A lot of this work that I'm going to be talking about today has been done in collaboration with the group of Professor Debye-Waller, who's well known for a lot of his work on graphene and particularly high-resolution TEM of graphene samples. Everything I'm presenting today, or almost everything I'm presenting today, the images would have been taken on our Joule 2200 MCO, which is a dual aberration corrected microscope. Primarily we'll be looking at diffraction patterns today, but we've done a lot of work on this microscope and studying defects in graphene at low acceleration voltages. Okay, so I'll get on with the talk then. As I said, we're going to be talking about quantification of atomic vibrations in mono-layer graphene. So I'll start off by giving an introduction to some of the work that we've been doing over the last few years about concentrating on trying to understand defects in low-dimensional materials, and primarily graphene. I'll then talk a little bit about ambient temperature knock-on damage, because in order to understand the formation mechanisms and also the evolution dynamics of these materials, we have to understand the interactions between our instant electron beam and our sample. I'll then go on to talk a bit about defect creation dynamics at elevated temperature, and at this point I'll talk about some of the perhaps more qualitative results we've got when we've been looking at our samples heated up with the DENS holder, and then finally come on to the advertised topic, measuring atomic vibrations in graphene. Okay, so firstly, defects in low-dimensional materials. Obviously, defects are important in the physical properties of all materials, but I would argue this is particularly so in materials like graphene, just due to their low dimensionality. So if we have a defect in perhaps a graphene crystal shown here, or maybe a carbon nanotube, it has numerous potential physical implications. For example, it might change the chemical reactivity locally to the defect, due to the creation of dangling bonds, or a change in the high electron density in the vicinity of the defect. So we could imagine perhaps selectively attaching particular molecules to defect sites in our materials if we wanted to engineer nanomaterials. It's also going to have, any defects are also going to have an effect on the electronic structure of the material. If we create a defect in a nanomaterial, in graphene or a carbon nanotube, for example, there's going to be changes in bond lengths around the defect, and this will affect the electronic properties. There may also be pi sigma rehybridization, and also of course the defect will be just acts as a scattering center in the perfect crystal. Furthermore, magnetic properties. There's been numerous theoretical predictions that certain defects in graphene will have a local magnetic moment. So this is perhaps interesting if we were to use nanomaterials in maybe nanospintronics applications, or one could envisage perhaps patterning arrays of certain defects across the graphene surface, and by controlling the distance between the defects, maybe one might be able to control the exchange interaction and have some sort of control over the bulk magnetization of the sample, let's say. And of course, any defects are going to affect the mechanical properties of the sample. So, if we're ever to really harness the power of nanomaterials, we need to understand the defects. We need to understand the formation energetics, and we need to understand how these things, how stable these things are over time and in real life situations. Okay, so a few words about some defects. So these are all TEM images I'm going to show in this slide, all taken at 80 keV and all at room temperature. So just go through the sorts of things when I'm talking about defects in graphene, the sorts of things I'm talking about. So this first one we see here, this is a stone whale's rotation. This is perhaps the simplest defect that we encounter in a graphene sample, and it involves no mass loss. There's no loss of any carbon atoms involved in this defect. Simply what happens is there's a breaking of bonds and a bond rotation, which creates this 5757 defect here, which we can see in the TEM image and is highlighted in this last image here. Stilwell's defect, that's one of the most common defects that we see in these in graphene materials. If we go up to one level of complexity then, come to the reconstructed monovacancy. So this is the simplest defect, which involves mass loss. So we eject, if one atom is ejected from the graphene lattice, then we get a bond formation, and we end up with a 5-9 pair, I believe it is, change in bond lengths around this particular defect. So the reconstructed monovacancy, or the reconstructed monovacancy, is the simplest defect that we encounter, which involves mass loss from the graphene lattice. We can then go up, we pop two atoms out of the graphene lattice, then we create dye vacancies. So on the left hand here, we can see a simple dye vacancy. If we then also have include bond rotations as well, so if we lose two atoms and then do numerous bond rotations, we can create increasingly complex defect structures in the graphene lattice. And we see these are observed in our room temperature experiments with varying frequencies depending on the energetics of the particular vacancy. So of course we can image and we can study these vacancies as just static vacancies, but we can also look to a certain extent at the dynamics of these things, how they evolve over time. So each of these images takes maybe a few seconds acquisition time, and then we also have perhaps another few seconds in order to dump the data out of the CCD into the computer. So we're looking at a frame rate of maybe one frame every 5 to 10 seconds. So it's not quite real time, but not a million miles off it. So at these timescales, perhaps surprisingly, we can see we can observe some dynamics of the defects. We can observe them, for example, over here, climbing and gliding across the graphene lattice. And we also see certain defects will evolve into other defects with time. Of course, the majority of the dynamics, it's very likely the majority of the dynamics that's going on is going on very fast, very fast speeds, so very short length scales, and obviously inside the TM we can't capture those sorts of dynamics. So it's somewhat surprising that we can see any at all, but we certainly can, and there's a reasonable amount we've published in the literature on the dynamics of defects. So at this point then we have to start to think if we're going to try and understand the energetics behind the defect formation, behind which defects are stable, the energetics behind how they evolve over time, how they climb and glide across our lattice. We have to start thinking about how much of what we're seeing is intrinsic to the material, and how much of what we're seeing is down to the way that we're performing the measurement. So it's the electron microscopist version of the measurement problem. We are, by imaging our sample, we're bombarding it with large numbers of highly energetic electrons, and this is inevitably transferring energy to our system, and we're creating perhaps this transferring energy to our system, and therefore we're not necessarily seeing the intrinsic behavior of our sample. Okay, and in fact in our case this is particularly true when we image our graphene at 80 keV inside the TEM. We would generally image with a broad, approximately parallel beam. In this illumination conditions, then we observe very few defects in our lattice. In order to observe defects, we have to focus our beam down to a small area, pump all of those highly energetic electrons into a small area in our graphene lattice. And we will leave that beam there for a certain amount of time, and then we'll spread the beam back to our approximately parallel beam that we use for our imaging beam, and observe whatever defects we've created, and then observe their evolution. And we have a certain amount of control over the complexity of defects that we can create. The longer that we focus our beam down on the sample surface, the longer that we have this defect forming probe, as shown in this schematic B here, the more complex the defects that we form are, the more energy we transfer to our sample, the more carbon atoms we knock out of our sample. So in order to understand this process then, we have to think about damage mechanisms inside the TEM. So there are numerous ways that you can damage your sample while imaging inside the TEM. I'm just going to talk about two, broadly lump damage mechanisms into two broad categories, which are electronic excitations or phonon excitations. So in general, in a material like graphene or in any metallic material, in fact, due to the high density of delocalized conduction electrons, any electronic excitations are very quickly quenched. So it's unlikely that that these are the cause of our damage mechanisms. And likewise, because these materials have very high thermal conductivity, any local heating again should be quickly dispersed across the sample. And there's been a reasonable amount of theoretical work trying to calculate the timescales involved in these sorts of things. So we then assume that our primary damage mechanism is knock-on damage. That is direct atom ejection due to momentum transfer between our instant electron and our target carbon atom. And of course, this can be thought of as being the extreme of a phonon excitation. We can calculate the maximum amount of energy that instant electron can transfer to our nucleus, to our carbon atom in our graphene lattice. Fairly simply, and it's determined just by the energy of the instant electron and the relative masses of the electron and the carbon nucleus. Indeed, this approximation is valid for relatively light, highly energetic particles. So once we have worked out then the maximum amount of energy that we can transfer from our electron to our carbon atom, we can then calculate what's known as a sputtering cross-section. So a sputtering cross-section is simply a probability. So it's a probability that interaction between instant electron and a carbon atom on a graphene lattice will result in the carbon atom being ejected from the graphene lattice. And to do that, we use the McKinley-Feshbach approximation, which is an approximation of Mott scattering, and is valid, is accurate for relatively light target atoms. So we're talking, as carbon is a relatively light atom, it's a reasonable approximation to make. And if we have a look at this equation, then there's lots of things in the equation, but importantly, it depends upon the ratio of the maximum energy, Tmax, that we can transfer from an instant electron to our carbon atom, and the threshold energy. So a threshold energy is simply the energy, the smallest amount of energy that's needed in order to break all the bonds around the carbon atom to allow it to be ejected from the lattice. And this can be theoretically calculated, and various theorists have calculated it to be of the order of 20 eV, and this was done from first principles or perhaps some Monte Carlo simulations, something like that. If we pump all these numbers then into our equation for our graphene sputtering cross-section, we can plot a graph which shows us the probability that we're going to cause damage to our sample, the probability that we're going to eject carbon atoms from our sample. And we can see that as we increase our accelerating voltage, which is along the x-axis here, we reach a threshold energy above which we start to cause damage. So according to this calculation, below something like 116, and an accelerating voltage in a microscope of something like 116 keV, we shouldn't be damaging our sample at all. As we've seen in the previous slides, all of that work was done at 80 keV. If we focus our probe down, we do cause damage. So there's clearly something missing from this model. This is a problem that Yannick Meyer addressed a few years ago. And he considered then what is the effect of, rather than having a static carbon atom, having a carbon atom which is actually moving, which obviously is a more realistic type of situation. Even at 0 temperature, even at 0 Kelvin, there will be a quantum mechanical zero-point motion of the atoms in the sample, so the atoms are never truly static. So the what Yannick Meyer proposed is that if you alter the equation for the maximum amount of energy that can be transferred from an instant electron to a carbon atom to include a velocity of the carbon atom parallel to the instant electron, and then put that into this number into our McKinley-Feshbach approximation, then you actually get a finite probability at low voltages that you will eject a carbon atom from the graphene lattice. So we can see here the red dotted line then in this plot is a theoretical calculation of the sputtering cross-section for C12 graphene at room temperature, so about 300 Kelvin. So it's assuming a Debye model for the phonon dispersion relation of graphene, which seems reasonable. Okay, so one would then, if you then look at how these curves change as you increase temperature of your sample, you pump more energy in your sample, and as you would imagine, the amount of damage you cause, you would expect to increase. So your carbon atoms are the higher the temperature of your sample, the more energy the carbon atoms have, the more they're moving, so the more energy that you can transfer from your instant electron, and these curves with increasing temperature shift towards the lower energy. So you would expect then, if we heat the graphene sample up and put it inside the microscope, even at 80 keV, we will really start to cause lots and lots of damage to our sample. In fact, that's not what we see. So here's a high-resolution TEM image of a graphene sample heated to 600 Kelvin using the one of the Debye-Waller heaters, imaged at 200 keV. So even at room temperature, when we try and image at 200 keV, we find a huge amount of defects in our sample. In fact, our graphene samples break down very rapidly, so we can't image them at 200 keV. When we heat the sample up, however, we tend to get we see very, very few defects, and we can image for prolonged periods of time, even at these much higher accelerating voltages. So there's clearly something missing from the previous picture of just these phonon-mediated damage mechanisms. There are clearly other temperature-dependent mechanisms going on which are competing with this phonon-mediated sputtering mechanism. So this was a slightly unexpected result. We felt in order to understand this, we needed to really understand, try and unpick the different mechanisms that were going on, different damage mechanisms and the different perhaps heating mechanisms that might be going on when we heat graphene at high temperatures. So just going to go off on slightly on an aside now and just quickly highlight one or two bits of work that we've done on heated graphene that perhaps don't pertain directly to the question of what these damage mechanisms are. We've done some work, Quang He in Professor Jamie Warner's group led some work on studying the edges of graphene as a function of temperature, the edge structure of graphene as a function of temperature. Now, edge structure is really important, particularly if you're interested in the electronics of graphene materials. If you have a graphene nanoribbon, then its electronic structure depends, can be controlled by the, in theory, can be controlled by the precise edge structure of the graphene nanoribbon, and the graphene nanoribbon can be either metallic or have a band gap, be semiconducting, depending on the edge structure. So being able to understanding how these the stability of edge structures with temperature is obviously a technologically important thing to study. So Quang found that as you heat the samples, the atomic structure of graphene edges actually changes quite drastically. So at room temperature, we see, broadly speaking, a equal proportion of zigzag and armchair, zigzag here and armchair here, edge structure. As the temperature is increased, see from this graph here, we see almost entirely armchair with very, very few zigzag edges, and we also see an increase in this reconstructed 5-7 edge. And this can be understood in terms of the energetics of the edges. And we've done some work with colleagues in Seoul DFT calculations, and broadly agrees with what we would expect. One slightly counterintuitive thing that came out of this study, though, is that we find that edges are actually more stable at higher temperatures. So as we increase the temperature of our sample, our edges are stable for longer periods of time. And again, if we think back to the sputtering cross-section arguments I was giving earlier, the phonon-mediated damage mechanisms, this seems again slightly strange. Another piece of work, this is pretty uncontroversial really, we're looking at the defect dynamics, so of a reconstructed monovacancy at high temperatures, and we found that as we increase the temperature, you increase both the glide and climb speed across the sample surface. So you're pumping more energy into the sample. There's more energy for the defect to migrate around your surface, as you might expect. And we also see some metastable intermediate states at high temperatures that we don't see at low temperatures. And most of this we can explain through the various energetics of the defects. Finally, then, the final thing I'll talk about is it's an example of a defect that we see only at high temperatures. So this is a partial dislocation, so in which the defect is spatially separated over a number of lattice constants by this stacking fault in the graphene lattice. And these partial dislocations occur due to competition between the formation energy of the partial dislocation and the strain energy of the lattice. We have never observed these at room temperature in the hundreds and thousands of TEM images we have of room temperature graphene. The reason that we think we see them at the elevated temperature is actually due to a mismatch in the thermal expansion coefficients of our graphene and then the silicon nitride support membrane on which the graphene is lying, which introduces an extra strain into our lattice. And we've done some, again, our collaborators have done some DFT calculations and have shown that within reasonably physical, within limits which correspond reasonably well with the physical experiment, that this extra strain in the lattice will enable the formation of these defects. Okay, so it's quite clear then that if we pump more thermal energy into our samples, we see slightly different behaviour. That's as you might expect. So we now want to try and understand how much thermal energy there is in our samples, and we then come to the question: how do we define that? So so far, I've shown images with temperature on the images. So this is 700 degrees centigrade. These experiments. Temperature is a thermodynamic property, and it's only well defined within the thermodynamic limits. That is, very large numbers of atoms. When we're looking at nanomaterials, when we're looking at trying to understand the temperature around defects, the very term temperature is poorly defined, and there's been a reasonable amount of work, theoretical work recently trying to define over what sort of length scales, what are the minimum length scales over which we can reasonably define a temperature. So I'm going to stop talking about temperature now broadly and try and pose the conversation in terms of something that I think we can define on almost arbitrarily small length scales, and that is the atomic displacement from ideal lattice position. So I would argue that this can be defined over length scales as small as just a few lattice parameters. The displacement of atoms from their ideal lattice position is in general quite a small distance, and the timescales of the vibrations are in general, again, very, very short. So unfortunately, we can't capture this information direct from TEM images. From TEM image, as I stated earlier, we're capturing the image over a few seconds. So we're seeing an average position over those few seconds, average position of our atoms. We can, however, capture this information from electron diffraction patterns. So an electron diffraction pattern is made up of a series of Bragg reflections from a periodic crystal. The intensity of the reflections then, if there's any disorder in the crystal, this will cause a drop in the intensity of the Bragg reflections. It will a drop in the number of electrons which are scattered into the various specific angles within our diffraction pattern. And this is increasingly the case at higher scattering angles. You can get out to these diffraction spots far away from the central spot. This is generally accounted for in scattering experiments by a Debye-Waller factor. So you generally account for this by adding an exponential decrease in the intensity of your scattering, which is written exponential minus 2w, where 2w is the thermal average of our scattering vector and our mean squared atomic displacement. So in principle, if we were to measure the intensity of our diffraction spots, we should be able to hopefully extract the Debye-Waller factor and from that get information about the mean squared atomic displacement of our atoms in our graphene lattice. And this then leads on to some quite fundamental questions about low-dimensional materials in general. It was long thought that the existence of low-dimensional materials was just impossible. Pales argued at the beginning of the 20th century that any arbitrarily small thermal motion, so from ideal lattice position in low dimensions, would cause a breakdown of long-range order, and that, of course, is essentially the definition of a crystal, that there is long-range order there. Of course, we know that graphene exists. We know that low-dimensional materials exist because we have them. So there's been a reasonable amount of theoretical work trying to understand exactly what it is that stabilizes these crystals. One argument has been put forward that if a limit is placed on the maximum phonon wavelength that the crystal can support, then this what we call singularity in the Debye-Waller factor, so this breakdown of long-range crystalline order can be avoided. Okay, so just discuss now how we go on to perform our measurement. So a few years ago now, researchers in the group of Chris Reagan at UCLA derived an analytical formula for the number of electrons which are scattered into each diffraction peak in a graphene sample. And this analytical formula includes a Debye-Waller factor, which is over here, and we also have a Coulomb screening length down here. Delta K here is our scattering angle, and then various parameters which are involved with the incident electron beam or details of our sample. SB here is our lattice sum. So we take our diffraction patterns. Here's a diffraction pattern taken at 80 kV from a graphene sample. This one's taken at room temperature, and we count the number of electrons scattered into each electron peak. And we can detect the number of electrons with varying by several orders of magnitude, and then we plot that as a function of our scattering vector, the length of our scattering vector. You can see here, this is data from room temperature sample, and we see these two broad trends of decaying intensity, as we might expect. Now, if we look at the details of the lattice sum for graphene, this can be fairly simply calculated to be equal to 2 cos pi by 3 v1 plus v2, where v1 and v2 are integer multiples of the reciprocal lattice vectors of graphene. And this lattice sum then, the square of this lattice sum, can only take one or two values. It can only take a value of 4 or 1, depending on the exact position of our diffraction spot. So this then defines our strong or weak reflections from our graphene lattice. If we then take this into account from our experimental data, we can just divide these strong peaks, the intensity, the number of electrons in these strong peaks by 4, and it brings all our data down to fit on one nice curve. So we then can fit this analytical equation to our experimental data and extract from that a Debye-Waller factor, mean square atomic displacement from the ideal lattice positions, and also a Coulomb screening length, inverse Coulomb screening length. So the inverse Coulomb screening length that we extract broadly agrees with theoretical calculations for what they should be, and we get a value of something like 15 picometers squared for our room temperature in plane mean square atomic displacement. Then we heat the sample up, and we perform the same measurement. We perform the same analysis at a variety of temperatures, as we might expect. As we put more energy into our graphene sample, the atoms are moving around, the amount of disorder in the sample increases, so the intensity of or the number of electrons scattered into each of our diffraction peaks decays, and we can see that from the experimental data here. As we go up in temperature, we get a faster decay in the intensity of our diffraction spots. So we can now plot the mean square atomic displacement that we extract from our diffraction data as a function of temperature over a wide temperature range. So these blue data is done with a homemade cooling holder, and the rest of the data was performed with the Debye-Waller heating holder. We can then, if we consider a simple Debye model for the thermal dispersion relation in graphene, we can then calculate a expected mean square atomic displacement, expected Debye-Waller factor, and fit that to our experimental data. Within this Debye-Waller model, then, we have to include, as I touched on earlier, a maximum phonon wavelength that our crystal can support. If we don't include this, if we integrate over all phonon wavelengths, the Debye-Waller factor just goes to infinity, as there's a singularity in it for arbitrarily small for any temperature, and in fact even for quantum mechanical zero point motion. So we can extract then a number for this maximum phonon wavelength from a number of something of the order of 3.5 nanometers, which seems surprisingly small. So one might expect that there is a physical limit on the maximum phonon wavelength that a crystal can support, and this may well be determined by, for example, the crystallite size, or something to do with defect density, for example, might limit that. Our samples, we know, are very, from room temperature TEM studies, that the number of defect density is very, very low. We also know that our crystallite size is of the order of certainly at least tens of microns, if not hundreds of microns. So exactly why this number is so small is why we're extracting such a small number for the maximum wavelength phonon that our crystal can support is the subject of continuing research. One other point that's worth noting is from the Debye model, if you take this to 0 Kelvin, there is still a finite mean square displacement. The atoms are still in our carbon, in our graphene lattice, are still moving due to a quantum mechanical zero-point motion. And if you calculate that, that comes out to something like 15 picometers squared. And this number has been calculated by a number of people using a variety of different techniques, and they come out with broadly the same number. From our experimental data, it would suggest that even up to temperatures of a few hundred Kelvin, the mean square atomic displacement, so the atomic vibrations, are dominated by this quantum mechanical zero-point energy rather than phonon contributions. I think that's quite interesting. So that's the end of my talk. I'll just leave you with then a list of all the people who have contributed to the various work we've done here at Oxford using the DENS heating holder. As I said previously, it's primarily driven by the Jamie Warner's group, who are very interested in the material science of of graphene and low-dimensional materials, and then Angus Kirkland's group, of which I'm a part, and we're more interested in some of the fundamentals behind the image formation and some of the more fundamental questions about microscopy. I'd also just like to draw attention to our collaborators who have done the DFT, Gundo Lee, led by Gundo Lee at Seoul University, and then, of course, our DENS colleagues who have helped a huge amount with the experiment, particularly in the early days of setting up these experiments and getting them up and running. We had a lot of support from Henny Zanderberg and Kang Zhu, both part of DENS. And with that, I'd like to say I hope you've enjoyed the talk, and thank you for listening.
Excellent. Thank you so much, Chris. It was a great talk, and I think graphene as a whole is such a hot topic at the moment that the properties of, obviously so many people are interested in, and it's really shown from the high impact papers that you guys have brought out, particularly in the last year. There's been a number of them, which we'll actually have on the website, linked to the videos, so if you want to check them out. And I love to actually see that how the theoretical models are challenged by guys like yourself that are doing the in-situ research. So that's really a great thing to see. So I've written down some questions. So one thing that I did note was that are you able to, I guess in a general term, make these kind of measurements with other materials?
In principle, yeah. So in principle, you will see, or in practice, you will see effects of the Debye-Waller factor in any scattering experiment. The reason why we chose graphene wasn't only because it's graphene, because it's interesting from a material science point of view, but it's also a very simple system. So a lot of the mathematics is much easier, essentially, when you have a nice simple lattice like graphene. So it would be reasonably straightforward to extend this to other low-dimensional materials, hexagonal boron nitride, for example. And we certainly are intending to do that. But when it comes to more complex bulk samples, the picture becomes much more complex. For example, the analytical model we have is only really valid for kinematical diffractions. That is when you only have you assume you only have each electron only undergoes one scattering event, and we think that's a fair assumption to make in a monolayer material. If we have a bulk material, that assumption falls down. So we wouldn't be able to make an analytical model. We'd have to look at doing much more comparison with simulations, and so it becomes significantly more complex.
Okay, thanks. Okay, and so you also discussed in-plane vibrations. Can you use this technique to extend to out-of-plane vibrations?
Yes, we certainly can, and we have done some work on that. So what we assume in this work then is that there is no contribution to disorder due to out-of-plane vibrations, and that isn't strictly 100% true. If we have some long-range corrugation of our graphene sample, then if you were to imagine a part of the graphene sample oriented like this with respect to the incident beam, any out-of-plane vibrations would then look like in a projection. It would look like an in-plane vibration. So there is a small contribution to the Debye-Waller factor that we measure, even from these numbers from out-of-plane vibrations. But we've done some calculations, and we think it's very small. What we can do is we can tilt the sample, and if we tilt the sample and then we start to see in our Debye-Waller factor, we see in our Debye-Waller factor all vibrations which are normal to the beam directions. When we tilt the sample, we start to see a contribution from the out-of-plane. That's experiments that we have done. They are somewhat more difficult to analyse for a variety of technical reasons.
Okay, and so from the different challenges that you would have experienced over the course of this number of experiments and this research, what would be that #1 challenge that you overcame, and then what advice would you give to the listeners to overcome the '1 challenge?
The #1 challenge, that's kind of tricky, because at every stage of the research there's been big challenges. I think initially when we first began the research, there were challenges involved in sample prep, and as an electron microscopist, if you don't have good samples, you can't even begin your experiments. I think most electron microscopists would tell you the key to getting good data is having good samples. So there's a lot of work done, again, this primarily by Professor Jamie Warner's group and postdocs and PhD students that he has on optimizing obviously the graphene growth, but then the transfer mechanisms, how to clean the graphene samples after transfer, and all these things. So I think that was the big difficulty. Now we're looking at some of these more fundamental issues. A lot of the challenges are involved in really understanding our experimental setup.
Okay, well, on the sample prep side of things, Could you just detail or elaborate a little bit more on how you actually did transfer and that process?
Yeah. So in order to, it's particularly important for the real space imaging, we have to have the graphene suspended over a vacuum. If we have graphene suspended over an amorphous material, we just don't get the contrast. So we can't image the graphene lattice. So when we receive the dense chips, the first thing we do is we take them to a fib, and we fib a series of thin holes in them. So these holes in the windows. So the dense chips have thin, that we use have a thin silicon nitride viewing windows, and I think that's something like 5 nanometers thick silicon nitride, something of that order. So we take them to a fib, and then we fib in them slits which have maybe which are maybe a few hundred nanometers wide and a micron long, something like that. So we'll series we'll fib an array of slits in them. We'll then grow our graphene through standard CVD techniques, and we use essentially just a standard transfer technique by which you cover your graphene. So you have your graphene typically on copper, for example, it's grown by CVD, and cover that with a polymer, which uses a standard lithography polymer like PMMA, and then etch away the copper using an etching. And you then have your graphene attached to the bottom of your PMMA, and you can handle that. It's reasonably robust, and you can then transfer that to your dense chip. And so then we have the dense chip with graphene on top, and then the PMMA on top of that. And you can then remove the PMMA using standard techniques that are used in lithography. You remove it using acetone, for example. We've actually found that in order to get very, very clean samples, it's necessary to essentially thermally degrade the plane. So we just heat it up to something of the order of 350 centigrade in air and leave it there for 24 hours, something like that. And that gives us very, very clean graphene on top of the dense chips. We found that we were a bit surprised actually at how robust the chips were and how we could use reasonably standard techniques for graphene transfer. We didn't have to alter that too much actually.
Great. All right, well, last question. So what's next for you and the research, and where you wanted to take it?
Okay, so from my point of view, I feel that we have to, there's a reasonable amount of work to be done to really understand how the precise parameters of the microscope are affecting these experiments. So we're extracting this number of a few nanometers for the largest phonon wavelength the crystal can support. I guess, as I've said numerous times, in the talk, we don't know currently, is that number so small because of something to do with the material, or is it to do with the way that we're performing it? And actually we suspect currently that it is in no small part due to the way that we're performing measurements. So we're doing a lot of work to try and understand exactly how our measurement parameters are affecting our measurement. We would then, of course, like to extend it to other materials. It's also just the first step in understanding these damage mechanisms, because as we showed, there's not only this phonon-mediated knock-on damage that's happening in our samples. There clearly are lots of other things going on. Once we can really understand how much the atoms are moving in our sample, then we can account for the phonon-mediated knock-on damage, and then we can start to look at seeing if we can unpick some of the other damage mechanisms. That's where we're going.
Excellent. Well, thank you so much, Chris, for coming on board.
Pleasure.
I thank all the collaborators as part of all the research, Professor Angus Kirkland, and yeah, I really look forward to everyone seeing this, and we're getting it out soon. So thanks again, Chris, and thank you for the viewers.
Okay, thank you, Rand.